Welcome to Physics 30 Prep Fast Track. This is lesson 2-1 and we're talking about forces and Newton's laws. So what's a force? Well, it's a push or a pull. There are different types of forces: electric, nuclear, magnetic, and gravitational forces. And a force is a vector. That means that it has both size and direction. You can't just have a force of 5. It has to be a force of 5 in a particular direction. So it has direction, and the imperial unit of measure, the unit of force, is the pound. We don't use pounds. In physics, we use the metric unit of force, which is called the Newton, or in basic units, the kilogram meter per second squared. Just to get an idea of the magnitude of a Newton, a polystyrene foam cup filled with about 100 milliliters of water would require a force of 1 Newton to hold it up, or in other words, about 102 grams. So 102 grams of a substance has a weight of 1 Newton, in other words, would have 1 Newton of force of gravity acting on it. To hold that 102 grams, you would need to exert a force of about 1 Newton upward. Now that's on the Earth. On the Moon, objects are lighter, and therefore it would be less of a force. So when a force acts on a body, we call that the applied force. Other forces, such as friction and gravity, are applied forces but can act on a body and either add to or subtract from our applied force. So if you're pushing an object up, gravity is going to work against you. If you're pushing an object down or throwing an object down, gravity is going to help you. When you push against friction, friction usually works against you. Sometimes that's bad, but sometimes it's good. When you want to stop, it's good to have friction. And of course, when you have these different forces acting on a body, then they all add up to what we call the net force. So, for example, if a force of 10 newtons east acted on a body, and then you added another 10 newtons, so 2 people pushing with 10 newtons at the same time in the same direction, you would get a net force or resultant of 20 newtons east. All right, very simple. You add one vector to the other and you get a resultant of 20. When forces act on a body and they act in different directions, you would add the vectors in a diagram tip to tail. The second vector starts where the first vector ends. The vector sum is found by drawing a straight line from the starting point to the end point. So the vector sum of all the forces, as we said, is called the net force. So if you had a force of 10 newtons east and then another force of 10 newtons west, these two forces are going to cancel each other out. The resultant will be 0. All right, the net force is therefore 0. And of course, there's a simple mathematical description of net force. It says that net force is the sum. This symbol represents the sum of, and so we've got the sum of all the forces. Depends on how many there are. There could be a bunch of forces. Sometimes there's only 2. In this case, there's only 2. There's the force pushing to the right or to the east. There's another force pushing left or to the west. And of course, these two forces, we make one positive, we make the other one negative, and we add them. Some people like to subtract vectors. I think it's a good idea to add vectors and give them the proper sign notation. So we're saying that east is positive in this case, and west is negative. When you add positive 10 to negative 10, you get 0 net force. So an object that's experiencing these two forces at the same time wouldn't have a change in motion because it has no net force acting on it. Now, again, when forces act on a body in different directions, you add the vectors in a tip to tail. The vector sum is the resultant, as we mentioned earlier. The vector sum is called the net force. Now, in this case, if a force of 10 newtons east acts on a body, and also a force of 10 newtons south acts on a body, then, of course, you have two-dimensional, not motion, but two-dimensional forces. And so the resultant of these two forces is going to cause an object to move not only to the right or not only to the east, but also towards the south. The resultant will be determined by using Pythagoras and trigonometry, just as you did with previous examples of motion. We would take 10 squared plus 10 squared equals c squared, or c squared equals a squared plus b squared, and we would solve for the resultant. We could also determine the angle. In this case, it would be 45 degrees. All right, we already mentioned that Isaac Newton developed the idea, a concept of gravity. He didn't invent it, but he invented the understanding, or the concept that helps us to understand. And he discovered the relationship that gravity applies throughout the universe. And he also explained why objects accelerate when he came up with Newton's 3 laws. The first law is very important. It says, an object in a state of uniform motion, that means moving at a constant speed. So an object undergoing uniform motion or constant speed, or at rest, so it's either sitting or it's moving with a constant speed, will remain in that state. So if you're at rest, you will remain at rest. If you're moving at 5 meters per second, you'll remain at 5 meters per second, unless what? Unless acted upon by an unbalanced, and in other words, a net force. An unbalanced force is a net force. And so what we're saying is you can't change velocity without a net force. Very important idea here. You cannot change the velocity of an object without exerting a net force on it. And of course, some consequences of the first law in your car, you can't speed up or slow down. So if your brakes don't work, then guess what? You're not going to slow down when you need to, unless, of course, you're going up a hill or something. On your bicycle, you cannot change direction without a net force. So often if you're riding your bike and let's say it's a little bit slippery out, you could possibly hit a slippery patch and you'd want to turn, but your bike would say, no, there's no friction to make me turn, there's no net force to make me turn, I'm going to go straight, and you could crash. And of course when walking, if you are standing still, you cannot start walking without a net force. So if you were on a perfectly frictionless surface, which is very difficult to actually create, but if you were on a very slippery surface, and think back to the movie Home Alone when the little kid iced the steps and then the guy stood on the steps, and of course no friction because of the ice, and they all they landed on their heads. That's an example of needing friction. You cannot stand up on an icy surface if there's no friction. All right, so in order to move from one place to another, you need to have a little bit of a net force. So that's the first law. The second law basically takes the first law and says, okay, I understand that if there is no force, net force acting on an object, it won't change its velocity. What if there is a net force acting on the object? Well, then it will change its velocity, and of course that means it's going to accelerate, because acceleration is defined as the change in velocity over time. The size of that acceleration will vary with two things. One is how big is the object that you are pushing, and how big is the net force that's acting on the object. So those two have to be considered, and Newton put that into mathematical form. He said that acceleration is equal to the net force divided by the mass. What he means is that as the net force gets bigger, so does the acceleration. This little symbol here means proportional to. So that means that acceleration is proportional to the net force. If the net force gets bigger, so does the acceleration. Now he also said that acceleration is proportional to the inverse of the mass. And what that means is as the mass gets bigger, the acceleration will get smaller. And that makes sense if you think of applying a force on a book. If the book is twice as big, the same force will not accelerate the book as quickly. Or in football, if you run into a 200-pound football player, you're going to accelerate him or her a certain amount. If you run in with the same force into a 300-pound football player, that football player that's 300 pounds is not going to accelerate as much because he has a greater mass. The bigger the mass, the less the acceleration. When we put those two together, we get what is called Newton's second law. This is the mathematical form of Newton's second law. And so as the force gets bigger, so does the acceleration of the mass. As the mass gets bigger, it has more inertia. Inertia is the resistance to change, and therefore a bigger mass is harder to accelerate, and more mass means less acceleration. All right, that's Newton's second law. You can do lots of problems with Newton's second law because it involves acceleration and mass and net force, and therefore you can also use kinematics. Once you know what the acceleration is, you can then use kinematics to find things like initial final velocity, time, and displacement. So as I mentioned, because the second law helps us to find acceleration using the net force and the mass, we can use that acceleration in kinematic motion problems. So we have, of course, the four kinematic expressions at the top. If you know the mass of an object and can determine the net force, you can calculate acceleration. And once you know the acceleration, you can then find initial or final velocity, time, or displacement using kinematics. So the top four equations are all using acceleration, and of course, you know, if you don't have acceleration, you can still use this guy. If an object is falling due to the force of gravity acting, all right, when you drop an object, the downward force of gravity is the applied force due to gravity. If there's no friction, then the frictional force is zero, or even if there is friction, you add the downward force to the upward force, the net force will give you an acceleration. If there is no friction, then g will be 9.81. So these can all be used not only to use Newton's second law to find the acceleration, but once we find the acceleration, then we can use these four kinematic expressions to find other bits of information as well. So very useful to have Newton's second law to help us with our kinematics. And finally, Newton's third law is the most widely known or quoted. It basically, you know, some people say things like, for every action there's an equal and opposite reaction. That's a very common statement of the third law. Newton's third law, we like to talk about forces instead of actions, but it's in some ways the same thing. If an object exerts a force on another object, the second object will exert a matching force in the opposite direction. Think of this for a sec. If you were to touch the wall or touch the table, as you touch the table, what does the table do to you? It touches back. And if you touch the table with a hard force, the table will touch back. If you slam your fist down on the table, the table will slam your fist back with exactly the same force. And so you may have heard it expressed as any action is accompanied by an equal and opposite reaction. We like to say in physics, any force is accompanied by an equal and opposite force. That means it's equal in magnitude, but opposite in direction. And so if you touch the wall touches you. If you fire a gun or a shotgun or any kind of a gun, the gun exerts a force on the bullet exerts a force on the gun. As the bullet is pushed out of the barrel of the gun or the rifle, the bullet actually gives the gun a kick. And sometimes if you don't hold your rifle or gun properly, then you can get a sore shoulder. And the earth exerts a gravitational force on you. You're being pulled down, but guess what you're doing to the earth? You're pulling the earth up. Thing is, the earth is so big, it doesn't really notice that very tiny little force that you exert. Or at least it's not greatly influenced by it. So when you turn your wheels to go around a corner, the tires push sideways on the road. That's what makes you turn. If there were black ice, you wouldn't be able to turn, because as you push on the road pushes back and causes you to go in a circle or in a curve. Black ice means there's no friction. If there's no friction, then as you push on the road, there is no push, all right, because it's frictionless. And frictionless means no applied force. So you keep going straight and you crash off the side of the road and have a big accident, hit a tree. All right. So that's not a good thing, but that's what Newton's three laws are all about. That you can accelerate an object by exerting a net force on it. If there's no net force, there's no acceleration or change in velocity. If there is a net force, then you will have acceleration. And of course, if you apply a force on an object, it will apply a force back on you.